Okay, welcome. We're going to start today by talking about algorithms and maybe change some of your associations that you might have with the word. I think that people tend to think about algorithms as being associated with computers. And while that's true, algorithms are a little different from simply something that happens within a computational environment. So we're going to just maybe demystify algorithms a little bit, and that will ultimately wind up being important for the class. Okay, so what is an algorithm? At its most basic, an algorithm is really a set of rules or procedures that can be followed step by step. Nothing too complicated about that, just the reasons that algorithms tend to be something we associate with computational environments is that computers are very, very good at doing things in a very procedural step-by-step way. They're not particularly creative, but if you do give them a series of rules, they know how to follow them. We're interested in this class in algorithms that yield emergent structures that look like they've been designed, but are instead simply the result of executing these step-by-step rules. And as I said, these algorithms that we're talking about don't necessarily have to be happening within a computer. So this class is not going to involve any computer programming. Don't worry about that. Or if you were hoping for that, then I'm sorry to disappoint you, but that's not something that I teach. But what will happen is that we will use the same principles that occur within algorithmic thinking, and we'll be able to produce designs that appear like they have been sort of planned and designed, but really they're just coming about through these step-by-step rules. Okay, so to give you an example of what I mean by things that don't have to happen in a computer, let's just think about games for a second. So in the game of dominoes, you know that there are certain allowable rules of play. And as you execute these rules, matching tiles to tiles, turning tiles when they're a double tile, you begin to see an array of patterns that are created by the domino tiles stacking next to one another. And there's a kind of a logic and coherence to this pattern. But it hasn't arisen because someone has sort of set out in advance to say what that pattern should look like. It arises because of this sort of simple series of step-by-step sequences that you would follow. Moving on from there, we can think about the game of Carcassonne. Some of you may have played Carcassonne before. It's a great game if you've never seen it, great for lockdown in the time of COVID-19. It consists of a series of tiles, and the tiles have got different illustrations. So some will include a little bit of road, some might include a bit of a town, a fortified town. There are tiles that contain bits of river and tiles that contain important buildings like churches. And so what happens is that you have a table and you put down a tile, and then the next person can put down a tile, but it has to be a legal play in that you can't have a road fragment crashing into a city fragment with no sort of road that's leading up to it. The tiles have to become unified as they merge and create a coherent landscape, and we'll see what that looks like. So here's an example of a landscape that is created by these sort of step-by-step procedures of placing these tiles in a way where you're abiding by the inherent rules of the tiles. And there aren't that many rules, just roads are matching with roads, cities match with cities. You can't have things crash into a context where they're not meeting up with something. And yet, through these simple permissible steps of play, we wind up getting a design of a countryside out of these various components. Now, it's not designed in terms of it having a particular functionality, but when we look at the overall picture of the landscape, it feels coherent to us. It feels like in some ways it could have been planned, it might have been drawn. You can imagine someone saying, oh, I'm going to draw a landscape. Where will I start? Where will roads go? And drawing it out sort of from that top-down perspective. Or when I say top down, I mean sort of like having a vision of something and then you draw it. But here, no one's really thought about it. At any moment, the landscape could have proceeded differently, just according to when you've placed a tile that then constrains the next possible tile that could be played. And eventually you wind up with this kind of coherent looking array of tile pieces. Okay, so pretty straightforward so far. There's nothing scary about that as what an algorithm might be, or that people worry that there's a lot of discussion about algorithms and computers, and should we be afraid of algorithms, and algorithms are controlling us. And you know, there's some legitimacy to those concerns about how algorithms might be applied in our lives. But an algorithm itself as a series of step-by-step rules shouldn't be frightening to anybody. Okay, so I'm going to look at a few more games, and then we're going to sort of start to veer this a little bit more towards things that we think about in design. But kind of getting closer into design, Spirograph is a very interesting algorithm. We saw how the tiles can create some constraints. In this case, we have a set of interlocking discs that you use a pen. It goes into a little slot or hole on the disc. There's a number of different holes on that disc, so you can place your pen in different positions. And then these circles have got teeth, and so they are able to sort of interlock with an outer loop. And you sort of roll the inner circle within the outer loop with these teeth locking it in place. And that starts to generate a constraint for the pen movement that creates a series of loops. And what's interesting is that you can see how many different sort of loops, how many circles there are in the game, but with only a few different kind of possibilities for the size of the circles and where you can put your pen and the size of the outer loops, you're able to generate a whole host of different kinds of patterns from this sort of simple kind of kit of parts, which you can think of acting as a kind of set of rules that constrains permissible movements of the pen, those rules being constrained by the size of the circle. So this is just a small sampling of how these simple rules are able to generate very, very complex patterns. There's basically an infinite array that you would have difficulty exhausting if you were sort of sitting and drawing with your Spirograph set for years of all the different kinds of patterns that you can produce. And of course, you can think about how many variables are at play. So you have like the variables of the sizes of the circles, and then the positioning of the pen, and then you have the colors of the pen acting as a kind of a third variable. And when we put these variables together, basically we have what we could think about as a generative drawing algorithm. And when I say generative drawing, what I mean is that the rules of that kit of parts are effectively what is productive, what is a source of creativity for what emerges as patterns. I don't have to sit down and think, oh, how can I draw 1,000 different patterns? If I were to give you the assignment and even just say, I want you to draw 50 unique circular patterns, and you have a week to do it, and they all have to be interesting and beautiful, you would think, oh, this is a tedious, burdensome assignment. Why is my professor being so mean? But if you have a Spirograph set, you just sit down, and the rules themselves wind up having a kind of productivity for you. They wind up being generative. They wind up kind of creating an explosion of possibilities that you might not imagine, but the rules themselves wind up being productive in terms of what can happen. All right, so I would encourage you all to pick up a Spirograph set if you don't have one already and play around with it. Other kinds of generative rules, this one is just sort of fun because it's supposedly a drawing of a subway map, or when you look at it, you would think it's a drawing of a subway map, but really it is a code where you translate sentences into different kinds of lines and dots on the line and names of stations on the line. And that code then allows you to translate sentences and produce a subway map from these sort of one-to-one relationships between the rules of the code and how those rules of the code wind up being translated into marks on a piece of paper. And again, when we're having to creatively think about making marks on a paper, that's putting the cognitive load on us to be creative and productive. But in this case, the rules of the coding produce productivity in terms of saying, okay, well, gee, I never would have thought to move the line this way, but the rules are telling me to move the line in a particular direction. Just so you know what the rules are, and apologies because the graphics are terrible. This is a blow up of a very, very tiny image on a page. But effectively, the generative code that created that subway map is that you type any sentences and then you go and you analyze a sentence, and there's certain rules. So keys that don't have any special kind of characteristics, it's just a line. But every time you begin a sentence, that's sort of the random start of the trajectory of a subway line. And then there's rules for, well, you put a station when you get to a letter O. And then in order to get the name of the station, you look at the last 7 type letters, and that becomes the name. And if you have a hyphen somewhere, that becomes an airport symbol. So you just basically take any sentences and translate these one to one. And ultimately, you know, I don't know how many lines there are. Maybe there's a dozen lines. So that would be the equivalent of a dozen sentences, just sort of starting and following the rules and seeing where those lines wind up by following these kind of series of step-by-step instructions. So again, you can imagine doing that by hand, and that would take a fair amount of time to do, to kind of not make any errors, to remember it. And the reason that algorithms work effectively in computers is that the computer is taking that kind of very mechanical one-to-one translation and doing it for you. Okay, so in terms of a little bit of the history of going from these processes where we take something that's maybe very mechanical and repetitive and translate that into something that can happen into a computational environment, I want to just orient you a little bit to the history of the digital computer punch card. And I think most of you probably know that this initiated originally from weaving technologies, and that you can imagine that when you're weaving, that basically there is a weave, the pattern that you want. And so the first image that we see, that's the outcome, that's the what the rules generate. But then if you're a weaver, you would have instructions for creating that pattern, and those instructions are essentially a numerical description of, well, you count this many. And I'm not a weaver, although I did do something years ago called ceinture fléchée, which is a different cassage that the voyageurs in Canada would make, and that involved also doing different counts in order to get different patterns. But patterns are generated because you sort of have a code where you say, all right, well, if I go back and forth 6 times, and then I have to drop a thread, and then I introduce a new thread into the pattern, and then I go another 3 lines, and then I, you know, drop another string and then pick up a different string. Those are the kind of the sequence that you would follow in order to create a pattern. And as it is an algorithm, because you have a series of rules that you have to follow, and then you have an outcome that of the pattern that emerges from following those rules. If you introduce variations into how you the number of counts you have, then that is what introduces different kinds of patterns, in the same way that the different circles moving in the spirograph produce different kind of sizes of loops, and then you get different sort of emergent features. So there's a whole host of different patterns of numbers of lifting and dropping strings and weaving that are very, very productive in terms of the richness of patterns that can be produced. All right. I'm going to pause me for a second, and I'm going to go to a video where you can see a little bit about the relationship between weaving and how that process of sort of the weaver themselves having to be able to do this physically, how that became translated into a physical process that would do that work for them. So I'm just going to pause, and I'm going to move to another recording. Okay, here we go.
This is a mechanical jacquard loom. This technology was developed in France in 1803 by a weaver named Joseph Marie Jacquard. The key thing about this loom is that it controls every warp thread, the threads that go from the front to the back of the loom, individually. Because it can do that, the loom can create very complex, fancy patterns in the cloth more quickly and with greater accuracy than the technology available before this loom was developed. These cards are what carry the instructions that are read by the apparatus on the second floor that tells the loom what pattern to create. The holes in the cards are read by a series of pins up in the apparatus, and those holes tell the apparatus which threads down here should be raised for each pass of my shuttle across the warp. Some of you might recognize these cards as looking similar to computer punch cards. Back in the early days of computer technology, punch cards carried instructions that told the early computers what kind of calculations to do. So this loom is the great-great-great-grandfather of the computer technology that we all use today. And that technology started with a machine that produces cloth.
Okay, so she leaves off by speaking about how we go then from the Jacquard punch card, which is a mechanical kind of on-off, to computer cards, which also have these little holes in them originally. I don't know if any of you ever saw a computer punch card. There was always the panic when I was in high school of someone dropping their stack of cards and then somehow their rules would be all out of order, so then they'd have to restack them. It was always a disaster. We don't have those problems now today. But the punch cards basically take what was a mechanical process of either sort of saying, all right, well, the rod can either go through or not through, and that mechanical process of the rod going through the card or not going through the card is what then either lifts a string or doesn't lift a string. That's translated into the digital environment of the punch card being either a 0 or a 1, activating a process or not activating a process in terms of coding language. But when we think about that coding, it's just worth bearing in mind that the process is still just a rule-based process, whether it is in a physical environment, the mechanical on-off, or whether it's in the digital environment, the zeros and ones that are controlling things. It's still just it's just a rule-based process that is sort of saying, do something or don't do something. And that series of rules is what allows us to get kind of this sort of richness of outcomes. All right. So to think a little bit more about this, I just want to talk a little bit about this idea of should we be afraid of algorithms? And I mean, I don't want to beat this topic to death, but it's just interesting to me, this idea of fear surrounding computers and what algorithms are doing and how algorithms are controlling us. When you can think, well, is it really algorithms that we're speaking about? There may be something that we need to fear, but I don't know if it's algorithms in and of themselves, in the same way that a generative pattern for making a weave for a material isn't necessarily something that we should be afraid of simply because we've coded the series of rules into a set step-by-step sequences for making something. So we can think of an algorithm as being like a recipe, right? And so in a recipe, we might have step 1 of the recipe is combine ABC, milk, egg, flour, for whatever reason. Pick anything you want, and there's probably D, E, F, G as well, but for simplicity. Step 1, combine ABC. Step 2, if lumpy, then add more A. So, you know, add more milk if it's got too many lumps. Now, this would be kind of a conditional feedback rule. So you check on the reality that you've produced, and then you say, well, is the reality sort of matching a desired goal, a desired outcome that I have? If it is, great, keep going. If it's not, well, then I have to do more of something or maybe less of something. Step 3 might be bake for 20 minutes at 350. Step 4 might be that then to, again, do this reality check. If it looks slightly brown, great, my cake or cookies are done, remove. If it doesn't look brown, then bake for 5 more minutes. So you can have these conditional sorts of rules where you sort of are checking, getting a feedback on where you are in the process, and then doing more or less of something. So we can think of a recipe as being a step-by-step code that is used to produce something that we want to eat or consume, right? So if we think about when do we repeat a recipe? or not repeat a recipe. If I make a recipe and I taste it and it tastes terrible, then I won't make it again. If I make a recipe and it tastes wonderful, I think, great, I'm going to do this again. So the question to me is the recipe controlling me because of the fact that, oh, it's encouraging me now to repeat that recipe and do it again? Where does the recipe sort of power end, and where does my sort of volition of doing something begin? And this sort of gets to this question of what role are algorithms playing in our lives. So should we be afraid of recipes? Like if we really love a recipe, then should we say, well, the recipe is controlling me. I had no choice. I had to eat that those 20 chocolate chip cookies because they were so good. So when you're on the computer and it says, step 1, show you ads A, B, C, and then step 2 would be, well, if I click a lot on ad A, then maybe, give me more ad A's because clearly I'm interested in that. If I don't click on them, then maybe try to show me some different ads that I'm going to click on. Sort of like, that same kind of check and monitoring. The algorithms might monitor the time that we spend on ads, and then if we're spending more than a certain amount of time, then we're going to get more ads of that sort of character. And if we're not spending time on ads, then it might sort of do some random changes. In the same way that if I'm making a recipe and I make it with raisins, but then my kids don't like raisins and no one eats them, then maybe the next time around I make them with chocolate chips and go, okay, wow, these were really successful. A lot of the internet is simply composed of algorithms trying to figure out what we want to consume more of, in the same way that recipes are trying to figure out, what are we enjoying consuming more of, and then, in that environment of consumption, we are also involved in participating in terms of how that algorithm is evaluating the adjustments that it needs to do in order to meet our needs in the best way possible. Okay, one last quick example, and this is really in order to think a little bit more about when we think about algorithms, are we thinking about something that can be physical, or are we thinking about something that is computational? So what are the rules for passing this class? We could say, well, if a student's grade is greater than or equal to 60 points, then I'm going to print pass, stamp it on their transcript. Else I'm going to print fail or something, fail. So, but don't worry, you're all going to pass the class, I'm sure. So what I want to do is I want to do this in a way where it involves a physical process, as opposed to my running it through an Excel spreadsheet. Say I don't want to program and I don't like Excel, I've never figured out how to use it. I actually love Excel. But we could say I'm going to rig up, I'm a strange professor, I'm going to rig up a sort of a scale on my desk. And this is going to be an analog grading computer. And when I say analog, what I mean is that it's not digital, it's actually mechanical. In the same way that we had the mechanical loom that is sort of enacting a process that's rule-based, I want to have an analog grading computer. It sits on my desk. It looks like a seesaw, and I've got a bowl on one side, and I put 60 marbles in the bowl, and that's your pass threshold. If you can get to 60 marbles worth of points, you're going to pass the course. And then on the other side, I've got 3 little bowls that are sort of balancing, well, not balancing that yet. And they're assignment 1, 2, and 3. And when I read over your assignment, I put a marble in bowl number 1. I put 3 marbles if I think you did not so great. I put 6 marbles if it's just a pass. I put 10 marbles if I think you're doing fantastic. You're all going to get 10 marbles. And I do this for assignment 1, 2, and 3. And the whole time, your transcript is sort of sitting face up on my desk. I hope you appreciate my beautiful illustration of this, by the way. But there's a stamp that's hanging off one end of this seesaw, and it's got a stamp on it. And as I put marbles into the bowls, and it starts to sort of balance off that pass threshold, eventually it's going to stamp your transcript with a pass. So there we go. We now have an analog grading computer on my desk because I don't know how to add other than with marbles. All I know is to be able to say, I think that was a 6 marble paper, just at the pass threshold. Hopefully you get at least 7 or 8. Now, what's interesting about this example is that what if no one is passing maybe I'm marking really too hard, and it turns out that no one has more than 50% of the passing threshold. Well, then I can just remove marbles from my pass threshold bowl till it gets down to 50 marbles instead of 60 marbles, and that way some people will pass the class. Alternatively, if I'm grading too hard, I can say, well, the pass threshold is going to go up. You're going to need to have 75 marbles to get a good grade. Hopefully you're not losing your marbles. I don't know, I'm going to make a bad joke watching the video, but all right, what I want to say here is that in this analog grading computer, my whole point here, other than talking about passing the course, is that there's some sort of critical difference that is being analyzed. Weight here is the critical difference that we're looking at. When we get to a critical weight, we have an effect, we have a pass. If we don't reach that critical weight, that 60 balls in the bowls, then we fail to enact something. And most of complex systems involve some rule being activated once we move past some sort of critical threshold. So whether a rule is activated or not can be a conditional rule, which is really, really important. There are rules that are kind of absolute rules, like when we have the dominoes, you do this or you do that. Then you can have conditional rules that involve difference. And difference is something we're going to come back to over and over and over again. So I want it to be very clear to you. A difference could be, well, it's not brown enough, it needs to bake longer. So, or a difference could be, well, you're clicking more on ads for new sofas versus ads for new coffee tables. That must be what you're looking for. So we're going to show you more ads of new sofas. There is some kind of difference within the system that is serving this role of feedback that allows the system to be able to calibrate what it should be sort of offering to you. The threshold could be the brownness of the cake, frequency of ad clicking, or it could be the weighting of the assignment scores, whether it's less or more. So difference is critical. Okay, we're going to continue on this, but that's it for sort of just this introduction to the general idea about what algorithms are. Don't be afraid of algorithms, and algorithms don't necessarily have to happen inside a computer. But how can we get our minds into this kind of algorithmic thinking? Thanks very much.